Let's look at the titration of a weak acid by a strong base. So again, thinking about the setup for this titration. The strong base, the titrant, is going to go in the burette, and a weak acid in solution is going to be in the Erlenmeyer flask. We're going to call that the titrant. We've already looked at the titration of a strong acid with the strong base. So let's compare the titration curves for the strong acid titrated with the strong base and a weak acid titrated with the strong base. The dotted line here represents the titration curve for a strong acid titrated with a strong base, and the solid black line with the numbers on it represents that of a weak acid titrated with the strong base. You'll notice that the initial pH of a weak acid is higher than that of the strong acid, and that is something that we have seen in terms of calculating the pH of a weak acid versus calculating the pH of a strong acid. And as you recall from the titration of a strong acid with a strong base, the initial pH is only dependent on the concentration of H+ in solution. So if we have the same concentration of strong acid and same concentration of a weak base in solution, we actually will have less H+ in the weak acid solution because it doesn't dissociate completely, whereas that of the strong acid does. Then, as we add base along the titration curve, the pH of the strong acid does not increase very much. As we add base along the titration of a weak acid, the pH does increase a bit more, and again we're starting higher, an higher initial pH, but there is a bit more of a difference between 0.1 and 0.2 in the weak acid versus that of the strong acid. You'll also notice that the equivalence point for the titration of a weak acid with a strong base occurs at a basic pH. And we're going to find that for every weak acid titrated with a strong base. The pH at the equivalence point will be basic. Beyond that, then beyond the equivalence point, the titration curves for both the weak acid and the strong acid titrated with the strong base are the same. So let's look at the 4 different points along the titration curve for the weak acid titrated with the strong base and consider what's in solution along those points. So at point 1, we have only the weak acid in solution. No strong base has been added yet, okay? So we're saying this is before any base has been added. And so the pH is dependent on the concentration of H+. As we know, pH is equal to the minus the log of the H+ concentration. And that H+ is coming from a weak acid. In this case, we're going to use a monoprotic weak acid. And we're going to be thinking about its equilibrium in water. So H+ plus H2O in equilibrium with H3O+ and A-. So point 1, we're simply considering a weak acid equilibrium. At point 2, we've now added some amount of strong base. So we've added some OH-. Okay? And so what we've effectively done is reacted our weak acid with OH-. This reaction occurs to completion, and we formed A- and H2O. And so what you can see is that in solution, we're going to have weak acid HA. That's from our initial concentration of weak acid before any base has been added. We add some base, some of that HA reacts away and forms A-. So we have both weak acid and its conjugate base in solution. Therefore, we have a buffer. So in region 2, anywhere between the anywhere after some amount of hydroxide has been added, but before the equivalence point, we have a buffer, and we can use the Henderson-Hasselbalch equation to solve the pH in that region. At point 3, we have the equivalence point, and so we know that at that point, this amount of OH minus that we have added is equal to the initial amount of HA. So the reaction of HA plus OH minus forming A minus plus H2O goes to completion. Essentially all of this HA has reacted away, and now we're left with A minus. But A minus is going to have an equilibrium with water, and it can reform some HA and OH minus. So this is the equilibrium that we are concerned about at the equivalence point of the titration of a weak acid with a strong base. And you'll notice that we said that the pH at the equivalence point of this type of titration is basic. And that is because in this equilibrium we formed OH minus. It makes the pH basic. At any point beyond the equivalence point, we have excess hydroxide. This is very similar to what we saw in the strong acid, strong base titration. And so this excess hydroxide is going to greatly affect the pH of the solution. So the pH is going to be dependent mostly, and for your purposes entirely, on the OH minus concentration. So while we do still have, in reality, this equilibrium happening, because we've added OH minus, okay, past this equivalence point, we effectively push this equilibrium back towards the reactant side, and this equilibrium is going to matter so little in comparison to simply the concentration of OH minus that's in solution. Okay. So let's work on an example. Let's take 50 milliliters of 0.0393 molar potassium hydrogen phthalate, which is a monoprotic weak acid. We put this in a flask and we titrate with 0.0964 molar sodium hydroxide, and we have a Ka. The first thing we're going to do is determine the volume that the equivalence point occurs, the volume of base added. I do this almost always for weak acid titration problems, because if I know the volume at which the equivalence point occurs, I can figure out where I am along the titration curve if I'm asked to then solve the pH at a different volume of sodium hydroxide added. Okay? So this is a useful first step for most titration type problems. So again, we are concerned about the initial concentration of weak acid. We're going to call our potassium hydrogen phthalate HA. Okay. We need to know its initial concentration. We know that at the equivalence point, the reaction of HA plus OH minus forming A minus plus H2O occurs to completion. Okay, so we want to know the number of moles that we start with of HA, and then calculate the volume of 0.0964 molar hydroxide that's required to get to that same number of moles that exists for the HA. So essentially we're going to use dimensional analysis. So if we start with 0.0393 moles per liter of HA, we have 50 milliliters of this solution, or 0.0500 liters, we know that for every 1 mole of HA, this will react with 1 mole of OH minus. And for every 1 mole of OH minus, we have 1 mole of NaOH. So I'm being incredibly detailed here in my dimensional analysis. We also know that the concentration of sodium hydroxide is 0.0964 moles per liter. And so when we cancel out, moles of HA cancel, liters of HA solution cancel, moles of OH minus cancel, and moles of NaOH cancel, we're going to be left with liters of NaOH solution. And then what we find is that we'll get 20.4 milliliters. In liters, this was 0.0204 liters. So what this is telling us is that it takes 20.4 milliliters of 0.0964 molar sodium hydroxide to reach the equivalence point. Okay. Inevitably, some of you may be tempted to use the dilution equation to solve this problem. Okay. You can't technically do that. All right. What you need to consider, what we're saying at the equivalence point for this reaction, the stoichiometry in front of HA times its molarity, that's HA, times its volume at the equivalence point is equal to the stoichiometry in front of the OH minus times its molarity times its volume. Okay? So this equation does quickly allow you to calculate the volume at the equivalence point of a titration. Okay, and then N, remember, is the stoichiometric coefficient for HA, for OH minus. Sometimes we do a titration when we use calcium hydroxide or magnesium hydroxide. And you have to be careful because the stoichiometry here matters, okay? Because for every 1 calcium hydroxide, we get 2 hydroxide. I don't actually recommend you use this equation. It does work. I prefer the dimensional analysis. This allows you to think through, dimensional analysis allows you to think through what is actually happening, the volumes, the stoichiometric relationship of this equation. This other equation that looks like the dilution equation isn't exactly correct. Now that we know that the volume of the equivalence point, I'm going to just take a note. Volume at the equivalence point is 20.4 milliliters, so that's the volume of sodium hydroxide required to reach the equivalence point. Now that we know that, we can start looking at these other calculations. The first thing is to determine the pH before any base has been added. So the only thing we have in solution is our weak acid. So we'll have our HA in water in equilibrium with its conjugate base and H3O plus. Okay. Again, the potassium hydrogen phthalate is what we're calling HA. We're going to use an ice table for this. So in doing that, we'll have an initial concentration of our HA. We'll have a change in concentration and our equilibrium. We know that the concentration of KHP, in this case our HA, is 0.0393 moles per liter. And our initial concentration of products is 0. Okay, this is just a simple weak acid problem. We're going to have minus X for HA plus X for A minus, and plus X for H3O plus. So then at equilibrium, we'll have 0.0393 minus X moles per liter of HA, X moles per liter of A minus, and X moles per liter of H3O plus. So then we can plug this into our equilibrium constant expression. We were given the Ka for this weak acid. It's 3.9 times 10 to the minus 6. This is then equal to the concentration of products, so that we have X times X, or X squared, divided by the concentration of reactants, and that's 0.0393 minus X. We can check if we can get rid of X in the denominator. Check the assumption that X is small relative to 0.0393. And to do that, the simplest way is to divide the initial concentration of HA, 0.0393, divided by the Ka, 3.9 times 10 to the minus 6. And if this is greater than 1,000, then our assumption is valid. And in this case, yes, it is. It's in fact over 10,000. So we can assume that X is small in the denominator. Then when we solve for X, we're going to get X is equal to 3.91 times 10 to the minus 4. And looking in our ICE table, X is equal to the concentration of H3O plus. And so if we take minus the log of 3.91 times 10 to the minus 4, we're going to get our pH, and our pH then is equal to 3.41. So we know that the volume required to get to the equivalence point for our titration is 20.4 milliliters of NaOH. Okay, just again a reminder. So in this problem, we want to know what is the pH when only 10 milliliters of sodium hydroxide have been added. Therefore, we know that we are before the equivalence point, but again, of course, after some base has been added. Therefore, we have a buffer. And so we can use the Henderson-Hasselbalch equation to determine the to determine the pH of this solution. But in order to use that, so the Henderson-Hasselbalch equation is pH equals pKa plus log of A minus over HA. Okay, concentrations of A minus over HA. We need to know what these concentrations are. And in order to figure out that, we need to know how many moles of A minus and HA are in solution in the total volume. And so we can calculate those concentrations. So we know that during the titration, the reaction that is being performed is our weak acid plus strong base, OH minus, completely reacts to form A minus and H2O. Okay, so we can set up a reaction table using moles. Okay, to figure out how many moles of HA and A minus are in solution after 10 milliliters of sodium hydroxide have been added. In order to do that, we're going to take the initial concentration of our weak acid, 0.0393, and multiply it by the volume, in liters, 0.0500 liters. And we're going to end up with an initial concentration of HA of 0.001965. The initial concentration, or excuse me, initial moles of OH minus are going to be the volume times its concentration. So the concentration is 0.0964 multiplied by the volume in liters, so multiplied by 0.01, and we're going to get 0.00964 moles of OH minus initially. So this is our before change and after table, our BCA table. So our initial moles of HA and our initial moles of OH minus go in the before line. We don't have any initial moles of A minus. In this reaction, I forgot a zero. We're going to get 0.000964 moles of OH minus. Before the equivalence point, the base that's being added needs to be the limiting reagent. If it's not, you did a calculation incorrectly or missed a zero, just like I did right there. So we're going to subtract 0.000964 from both OH minus and HA. And so we're going to end up with 0.001001 moles of HA. And in fact, we need to add the moles to A minus. So we add 0.000964 to A minus in the A minus column, although I've gone a little skewed here, but hopefully you know what I mean. So after the reaction happens, we have 0.001001 moles of HA, and we have 0.000964 moles of A minus. In the Henderson-Hasselbalch equation, we use concentration. So to find the concentration of A minus, we're going to take 0.000964 moles, divide by the total volume. We started with 50 milliliters of the HA, the potassium hydrogen phthalate, and then we added 10 mils of the sodium hydroxide. So we have 60 milliliters of solution, or 0.060 liters. So the concentration of A minus is 0.01668. The concentration then of HA is the moles, 0.001001, divided by the volume, 0.060, and we get 0.01607 moles per liter for HA. We can then put this into our Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA, but we need to know the pKa. We were given the Ka for KHP, for potassium hydrogen phthalate, or HA in this reaction. It's 3.9 times 10 to the minus 6. And so the pKa is equal to minus the log of that value, and it is 5.41. So to solve for the pH, we're going to take pH equals our pKa 5.41 plus the log of the A minus concentration, 0.01668, divided by the HA concentration, 0.01607. When we calculate this, we should get 5.39. And you'll notice the pH has increased a bit from the point before any base has been added. That's good. We initially started at 3.41 for the pH. We're now at 5.39. Okay, so it's kind of a good thing to step back and figure out if the pH that you calculate makes sense. The other question that I usually ask or get asked at this point is, do you actually have to calculate concentrations to go into the Henderson-Hasselbalch equation? Because you're essentially dividing both of these mole values, which are different, by the same volume. And technically no, because you're dividing by the same volume. you could use the moles and get the same value. But the root of the Henderson-Hasselbalch equation is essentially an ice table, and in ice tables we use concentrations, and so that's why I typically will stick with using concentration in the Henderson-Hasselbalch equation. Okay. So the next place where we can calculate the pH is at the equivalence point. Again, the equivalence point required 20.4 milliliters of NaOH. Okay, that gave us the correct number of moles to react with the initial moles of HA. And what we're saying at the equivalence point is that the HA plus OH minus reaction forming A minus and H2O occurs to completion. Our initial moles, and again, this is we're thinking about doing a BCA table here. So we're going to use moles. Our initial moles of HA, based on this concentration and volume, was 0.001965. We know by definition, at the equivalence point, we've added 0.001965 moles of OH minus. We're going to subtract 0.001965 from both the HA and the OH minus and add it to the product side for A minus. So then after this reaction occurs, we are left with 0.001965 moles of A minus. And from that, we can determine the concentration of A minus because we know the total volume of the solution. We have our 50 milliliters and our 20 milliliters. So if we sum that up, we're going to get 70.4 milliliters total of solution, or 0.0704 liters. So the concentration of A minus is 0.001965 divided by 0.0704 liters, and we'll get 0.0279 moles per liter. So to determine the pH at the equivalence point, okay, so far all we've done is figured out what is at the equivalence point. So we found that we've reacted away all of our HA with OH minus, we're left with 0 moles of those. The only thing we're left with is A minus. So the only species in solution that's affecting the pH, essentially, is A minus. And we know that that reacts with water. It has an equilibrium with HA and OH minus. Okay. We also know from our titration curve that the pH at the equivalence point of the weak acid titration with a strong base should be basic. And again, that's because of this equilibrium. So using an ice table, we can now determine the pH because we can calculate the hydroxide ion concentration, and from that we can calculate the pH. Okay, so in an ice table we're going to use initial concentration of A minus, 0.0279. We have no initial concentration of HA or OH minus. We're just considering what happens when we put A minus in solution, essentially. We're going to have minus X for A minus, plus X for HA, and plus X for OH minus. And so we'll get 0.0279 minus X for A minus, X moles per liter for HA, and X moles per liter for OH minus at equilibrium. Now, this is the conjugate base of HA. In the problem, we were given the Ka for the weak acid. We now have in our reactant side of this equilibrium the conjugate base. So we need to know the Kb for the reaction. Kb is going to be equal to 1 times 10 to the minus 14, which is the Kw value, divided by the Ka value, 3.9 times 10 to the minus 6. And that then is going to be equal to the concentration of products, x squared, divided by the concentration of the reactants, 0.0279 minus x. We can check our assumption, and what we'll find is that we can ignore x in the denominator. And when we finally calculate x, we're going to get x is equal to 8.46 times 10 to the minus 6 moles per liter. And from our ice table, we know that this is equal to the OH minus concentration. If we take minus the log of 8.46 times 10 to the minus 6, we will get 5.07. And so the pH is equal to 14 minus 5.07, which is 8.93. And again, we wanted our pH to be slightly basic. We got that, it's close to 9. And so there's a good chance we've done our calculation correctly. Finally, if we want to calculate the pH 10 milliliters past the equivalence point, we can do that very similar to the way we did this with the strong acid, strong base titration. Again, we know that the volume required to reach the equivalence point was 20.4 milliliters. So this is effectively saying we want to know what the pH is when we add 30.4 milliliters. We're going to use a reaction table. Here we're going to have HA plus OH minus reacting to form A minus plus H2O. Again, we're going to use the BCA. We know our before moles of HA are 0.001965. We're now adding 30 milliliters of 0.0964 molar sodium hydroxide. So if we multiply those values together, we get 0.00293 moles of OH minus. HA in this case is the limiting reagent, so we're going to subtract 0.001965 from both HA and OH minus. We can add it to the correct thing is to add it to the A minus plus 0.001965. But when we get down to actually calculating the pH, we're going to ignore the equilibrium with A minus. Okay, so after we're going to have 0 moles of HA, we're going to have 0.000966 moles of OH minus, and we do have 0.001965 moles of A minus, but we're going to ignore this equilibrium because it's going to contribute such a small amount to the pH. So we need to only consider the excess hydroxide. And again, we need to calculate the concentration of hydroxide. We take our moles, 0.000966 moles, divided by the total volume. So again, we have our 50 mils of start, our 30.4 mils of base that we're adding, 0.0804 liters. We get 0.0120 moles per liter. To find the pH, we'll do 14 minus the log of the pOH, which is, well, minus the log of the pOH, 0.012, and we'll end up with a pH of 12.08. So again, a very basic pH after the equivalence point.